yours.
Yeah, and like a disclaimer before I fully get started on this. This is a new topic, and I realize you're all like mostly MBA students or finance students. This is not a data or computer science class. And please stop me whenever you have a question. Just like ask me the question. The whole point of this is to give you a perspective and a foundation so you can use in the future. I don't want to talk of myself. So anything you don't understand, just stop me. We're flexible on the pace. I'm not coming here to just like power through a bunch of materials. I want to teach what I can, and I want us to go at the same pace. So please do stop me whenever like something doesn't make sense to you, or like something is confusing you, and that is fine. We're not expecting this class to.
No question is a bad question. No
Yeah,
question.
yeah, just like because your questions will help others understand as well, and it will help me explain better. So the whole thing is a good dynamic. So please do that. All right. With that, let's get started. All right, I'm gonna start with a question. Imagine we have 94 publicly available characteristics since 1954, which I imagine is the year that S&P 500 was put together. And these are generic sort of accounting data that we look at. We've seen Hugh mention it a bunch of times in his analysis. We have stuff ranging from the present accruals, leverage, capital expenditure, the typical stuff, the beta, and we have 94 of these features for a historical 60 years or so, right? And the question I want to ask you is that we also have the quarterly and monthly returns for each of these characteristics for all the stocks in the S&P 500 over the past 60 years. Now, having that data, we have 60 years of data, we have these 94 characteristics, and we have the returns for each stock with those 94 characteristics at any point in time. My question is, can you predict our portfolio's return a quarter from now based on what you can learn from this 60 years of data? Do you think it's technically possible? Is the information there with that like 60 years of data? Is there enough information there to be learned, to be able to incorporate the relationship of all those characteristics from the betas, from all the other stuff, to be able to predict a return for a stock? Is that technically possible? Anyone have any ideas?
It's possible.
You'll get close. I don't think you'll obviously be exact because 60 years ago didn't have COVID in it, for instance. So you just never know what's going to happen in the future.
Very good point. That's actually one of the reasons that machine learning is extremely more difficult in finance. Anyone else?
I agree. You could probably get it, but yeah, there's going to be some sort of error term in there that you're not going to be able to get.
All right. So we can do this, and it's not going to be perfect. I'm glad we like settled on that foundation. And the way to do it is like the machine learning basically does this. And there's a recent paper actually published by a bunch of financiers or economists or whatever they're called, Empirical Asset Pricing by Machine Learning. This is a 2020 paper. It's very recent. And what they did was with this 60-year data, they trained a generally simple machine learning model, a bunch of different ones, the neural networks, decision tree, logistic regression. And they managed to be able to extract that information to be able to predict the return of a stock based on those 94 characteristics. And they developed a portfolio based on this simple 4-layer neural network machine learning algorithm, which you can see here in red. And it outperformed the S&P 500 by a good margin consistently. As you can see, it had an annual return of 27% yearly, like since 1987. And as you can see, the black line here is the S&P 500, and the red one is the machine learning algorithms trading, right? So there is information to be extracted there, and there is profit to be made. But this field is a lot more complex. but that is the general idea. That is why like a lot of these hedge funds and like are going this way, because there is information to be extracted, and machine learning is a decent tool to be able to extract that information and give us insight about the future. Now let's settle some ground rules here. We hear these words a lot, and I'm not really a big fan of sort of categorizing everything into like a whole basket, but it's decent to have an idea since it's like mentioned everywhere. What is artificial intelligence? It's basically what we assign to a bunch of techniques that will allow us to mimic human behavior. Under that is machine learning. And machine learning is something we're going to talk about in this lecture. We're not going to get into AI, but machine learning is part of that. And machine learning is the study of computer algorithms that automatically improve through experience. Generally, in other words, is the ability to learn without being specifically programmed. And deep learning is a part of machine learning which uses deep neural networks, which we will mention later on in the class. All right, and this is the current state of the industry. If you look at it, the landscape of the industry, obviously AI has been, and machine learning has been becoming extremely more popular over the past years, and we're going to talk about why in a little bit. But this is the extent that we see, and the finance industry has been a little bit slower to adapt, but they are adapting. Like hedge funds like Jane Street, Two Sigma, D-Shot, they're using these stuff. We even see like insurance companies and bankers using it to predict like credit defaults and pricing different premiums, and it's becoming more and more popular. Now, why is it becoming more popular? It is important to settle this here too, because these are basically the three constraints that this whole technology and methodology has. Machine learning generally needs data. And because of big data, because we've produced basically the majority of the data in the entire universe since the beginning of time in the past 10, 20 years, we have a lot of data. Machine learning also requires processing power, and the processing power technology has been increasing exponentially with Google's TensorFlow and with like NVIDIA's high processing GPUs. This whole tech is becoming increasingly more popular. And the last part of that is the machine learning algorithms, and that's just a mathematical algorithm. And a lot of them have been around for ages. Like the first ones, I believe, were proposed around the like 50s and 40s and 60s. So we had these algorithms available for a long time. The problem was that we didn't have enough data and enough processing power. For example, if you watch the video I sent you, the first machine that was built, it was this like giant size of a room computer that could only predict 1 and 0 with like 100 data points. Now, like we can do 10 times, a million times that even with our phone. And since we're talking about this too, which part of this do you think Google operates in from an investment perspective? Imagine we're trying to value the intangible assets of Google. Anyone has any idea?
Every part.
Exactly. Google has all the data in the world, the big data. They have the TensorFlow, which is like one of the most popular processing power tools we have. And they have research labs for the most talented people developing the best algorithms. Hence the value of Google. Google knows us better than we do. If you look at NVIDIA, on the other hand, they have a decent market share when it comes to GPU and the processing power. And that comes into play in their competitive advantage. All right, before we get into the actual stuff, why we added this sort of module here and what you'll get out of it. As I've mentioned before, the finance industry is adapting these methods. It has been slower than a lot of the other sectors, but it's happening. And funds, credit agencies, insurance banks, they're all trying to get use out of this technology. And we want you to become familiar with this concept and get you started coding. And this will be a starting point for those of you who would be interested in doing this in the future or adding this sort of module to your career techniques or career skills. And even if you do not want to add this, if you don't want to code in the future, if you don't want to become a data scientist in the future, and that is fine, This will give you an idea about what you're dealing with. If you're in a meeting like 2 years, 3 years from now from some hedge fund guys, and the guy's like, I'm doing NLP, this model's saying this, you will be able to call bullshit on that if like you look at the measurements and you're like, nope, this is just a sample bias. This is not training well. As Brian and Matt mentioned, like the error term in the finance industry especially is really important. You'll be able to understand what they're doing. You'll be able to understand, okay, Goldman Sachs is looking at satellite images to be able to predict Walmart's sales next year. You'll be able to understand how that dynamic works. And last but not least, this will like give you an idea about like one of the most important promising technology sectors that is going to come in the coming years, which is like AI and machine learning. And it is the basis for a lot of these cross-sector technological innovations that are happening. All right, so let's try and define our problem a little bit more specific and get into it. We generally have 3 types of machine learning here. The first one is supervised learning, and that is the one we're going to talk about in this class. In supervised learning, we generally have a bunch of features like the stock characteristics we saw in the beginning. And you have a bunch of labels. And these labels could be the returns, as we saw before. And you want to develop a model, you want to train a model, you want to train a machine that is able to predict Y by having X. You want to develop a function that can map from X to Y. Or in simpler words, if you had a bunch of data consisting of tigers and not tigers in pictures, you want your machine to be able to tell you this is a tiger. That's all you want. You know what a tiger is. You're not trying to, but you want your machine to learn from what you know to be able to predict the future. Another popular sort of machine learning approach is the unsupervised learning. And this is the part where you don't really have any labels. You just have a bunch of data. And the goal of this sort of approach is to learn the underlying structures in your data and whether they're similar together, or how they work, how close they are together. And what this sort of approach will give you, it will tell you like these 2 things are similar together. We're going to get deeper into supervised learning. Don't worry about it if the whole thing is a little bit confusing right now. And the third bit, which I'm not going to get into here, is that the reinforcement learning. And this has been gaining a lot of popularity recently, especially like in the, even they're adapting it in the finance literature. It's fascinating stuff. If you want to look into more recent stuff, I would recommend looking into this. How this works is trying to simulate an agent within like state and action pairs, and it will give an agent rewards depending on what action it will take in that simulated environment. The whole idea is that the agent will learn to make the best decisions if we train it right in that environment. The whole concept of like driverless, the autonomous vehicles, the whole purpose of the whole model behind that is reinforcement learning. They use this to do that. And generally, with our tiger example, the machine will be able to say, step away from this thing because it will kill you. Again, to put this into a little bit more perspective, the main difference between machine learning models and regular programming is that in regular programming, you have a program, you have a function, and you have a bunch of input, and you feed that into a computer script, and that computer script will give you an output. In machine learning, what you want to do is you want to give the input and the output to the computer, and the computer will give you a program, it will give you a model. And if that model is good enough, then you'll plug in that model here, and you get an output, for example, to predict the stock returns in the future. Any questions so far? Okay. All right. So let's get into supervised learning. As I mentioned before, the whole idea is we have a bunch of features called X, like those 94 characteristics that we saw before. And we have a bunch of labels. We know what the truth is. At least we know for some portion of the data. and we want to be able to create a map from X to Y. We want to create a function that is able to predict Y based on X. And you can have a bunch of different data structures. For example, this first one, again, is an example of supervised learning. This is actually becoming very popular recently, especially in finance. This is like, we're trying to, it's called natural language processing. Imagine you have this data point. The firm is facing a felony charge in courts. And in truth, you know this has a negative impact. Imagine you see this in a firm's 10K document. And you have this label, negative, and you have a bunch of these sentences. Then you want to be able to train a model on these samples, like imagine like 10 millions of these sentences with different labels. You want to train a model on this thing so it can predict, it can classify, it can understand what the negative and positive and neutral means. And after that, you can, from this point in the future, instead of reading your 10Ks, you can just plug it into the machine and, okay, this is a positive one, this is a negative one. Same thing with the tigers. This whole data set could be an image. It doesn't have to be just a structured data set. It could be a picture of a tiger and a picture of a not tiger. And you label it, okay, this is a tiger or not a tiger. And this is called a classification problem. Whenever our Y space is a discrete sample of things where we can count on one hand or two hands or whatever, it's not continuous. Whenever it's negative, positive, neutral, tiger, not tiger, 1, 0. This is what we call a classification problem, where we're trying to find an algorithm that will group different classes correctly together. But this doesn't have to be all of it in supervised learning. We also have the regression problems. And this is where our Y space is continuous. I believe all of you should have done some regression at some point in your quantitative finance classes. And that's basically what it is, regression and machine learning. It just takes a little bit different approach, and we'll talk about that later on. But the first problem we saw here, whenever those guys were trying to predict returns based on a feature set of 90 for accounting characteristics, that return was in a continuous space. It was just 1, 2, 3, 1.5, 4.5. It was just numbers like that. And I was trying to fit a line that could find that. Does this make sense to you? Okay, cool. One thing I do need to mention here, and I will get deeper into this. So like if you're not connecting with it now, that is fine. But after we train the model, we want to know how good the model is. We want to be able to, okay, how good is this model in detecting tigers? Because if that's the idea and you want to put that in a zoo, like you want to detect tigers out of their cages, and the model's wrong, bad things are going to happen. So you want to be able to tell, okay, this model works. Or you want to predict the markets. That's even a worse scenario. Imagine your model is predicting something, but that doesn't happen to be in reality. As Brian and Matt mentioned, like we always have the error point. And so you need to evaluate whatever model you're trying to create here. And generally the approach in machine learning is the data that you have labels for, the data that you know what the truth is, you will always try and split this into a training sample and a validation or a test sample. I'm going to use these interchangeably. You might want to get two, like they're different things, but for now, let's just say we need a sample that has that the model has not seen yet, the machine has not seen yet. And after you train a model, you want to be able to see how that model is doing on that sample that it has not seen yet. And because you have the Ys, you'll be able to see if the performance it's doing on that sample is any good or bad. I'm going to get into this a little deeper. I just wanted to hint this out because it will help us understand it. Any questions on this?
And Farhad, will you talk about in sample and out of sample? So tigers in that zoo versus tigers in a zoo, other than the one on which you are programmed, you know?
That is exactly correct. Like Brian said, imagine we train a model in the COVID era, right? And it's only in the COVID era. Like we have 9 months of COVID era, and we want to predict something in 2025. Is that gonna, and it works perfectly in the COVID era. It's like 100%, like estimates every stock return, perfect. Is that gonna work 5 years from now when we don't have COVID? Where
No,
the like
it's the
entire
time period bias.
yeah, time series are a lot more complicated, and we'll touch on that in our next
Sorry, no,
class a little bit.
I said time period bias.
Yeah, time period bias. But the same thing goes with the sample. Imagine if I look in this class and I'll be like, okay, I want to estimate the, I don't know, like the ages of people. And I'm gonna guess from looking at this sample that the entire population of the world, I don't know, 15 of them are aged between 20 and like 30, and one of them is ranged between like 40 and 70. And that's going to be my assumption for the entire universe. Is that a true assumption, or is it just a sample bias? Right? Well, we'll touch on this. This is a very important concept in the like machine learning dynamic, and we rarely see it in finance because the regressions they do in finance, they just use some p-value and they don't generally go on to like out of sample validation. But this is very important. And the idea is that you want your model to work in every sample. And obviously you're always going to have some sample bias. But the idea is like, if I only like look at this class and this class only, I'm not going to have any idea about what it is. But we'll touch on this a little bit later on. Any other questions on this thing? Okay.
Could you
Go.
speak a little bit more on bias? Because I was watching the videos yesterday and I was a little bit confused about two of them. In one case, bias is described as something that you can add a certain weight to it or remove weight to it to get a certain output. In another one, I think they said bias was the inability of machine learning to capture a true relationship. Could you please?
Oh, yes.
So
that is a little bit bad on their part. I guess a little bit bad on the mathematical literature. Cause like you've seen regressions, bro, right? Do you remember like there's a beta you calculate, and after that there's an error term they always write in the regression equations?
Like in the next slide, you can see it.
Yeah, I'll get into it. But what you need to do, like you are saying correctly, there's always, whenever you're trying to like say y equals 2x plus 2, they refer to that 2, the constant value, as a bias term as well. But whenever we say bias, we don't mean that. We mean the other bias, where like the machine is not predicting correctly. So whenever we say bias, it means that like the machine is predicting it wrong. But I'll get into that. That's a very valid point.
It's a very valid
really
question
noticed
because
before. Thank you for bringing it up.
because Rom, the question is the way we think of bias in human term is I am biased to somebody. A machine cannot be biased like that because anything which is systematic, the machine knows it can take it out. So essentially, but there are non-systematic biases, the biases which the machine automatically makes, which are kind of completely random, and those biases will remain. So you got a good point. It's a mathematical definition of a bias from a human definition of a bias. I mean, we could be biased to anybody not knowing a math. That's our problem, right? Because we are biased. A machine is not like that, because if a machine is, if you detect a machine has got a particular kind of bias, we can program it out. But any programming you do will introduce some other kind of a bias. So some kind of systematic bias always remains with any estimation.
Yes, another way you can see that, I think later on you will see the logistical regression. It's more like how you evaluate the results. When the results can be defined as you predict it's right, you predict it's right, and it's wrong, you predict it's wrong. And also that's possibility it's right, you predict it's wrong. So it's kind of 4 scenarios. That's kind of sensitivity analysis. So what you define the bias is something you get those wrong, something right, the model predicted wrong, and something wrong, the model predicts right. So that's two areas of the bias spot. So I think later on you will see in the logistical regression, some like sensitive analysis, you will see those kind of measures, how to measure how good your program is.
Is it something like false positives or
Yes.
false
Yes,
negatives that
something,
we
yeah.
Absolutely
usually
right.
Mathematically,
Yes,
yeah.
the
got it.
false
We're
We're gonna
positives?
get into those. We're
Type
like,
1,
Okay.
type 2, something like that.
yeah. We're
Okay.
gonna like we have a like whole segment about like measuring machine success, like with different the accuracies, like those true positives, true negatives, recalls, precisions, R scores, all that good stuff. The main thing I wanted to say here is that like it is important to understand that we have two sets, like one we train on, one we test on, and that is important to understand the algorithms. But the point you're bringing up, bro, is really great. And for now, whenever we say bias, I'm going to get into the equations as well. Have in your mind whenever the machine's wrong, right, in this discussion. But we'll touch on that a little bit later on as well. Any other questions? All right. Okay. So with that in mind, we have our training sample, and we want to map from X to Y. Very similar to what you've seen in regression. It just takes a different approach to find those things. And we have a variety of different models. We have the neural networks we're going to talk about here. We have logistic regression, SVM, which we're going to talk about a little bit. And the main equation we're trying to solve for is this thing. We want to find the W's, find the weights that can map from X to Y. It's basically a function. We just want to find the best W's to satisfy this function, to find the like most accurate Y we can. And the simplest form of this whole thing is regression. And regression tries to minimize the least square error. And that is what it's trying to minimize, and that is how it works. Let me talk about this chart and ask you a question. So this is the price of Ethereum based on the price of Bitcoin. I think it's over the past couple of months, right? And I just drove a linear regression on these things. I want to predict the price of Ethereum based on the price of Bitcoin, right? And I drove this equation out of it. My first question is, what does this equation try to do? Like, what is regression doing here? Why this line? How does it drive this line? Anyone can shed any light on that?
It's trying to minimize the distance between the points and that line.
That is absolutely correct. Thank you, Matt. Exactly. It is trying to minimize the summation of distances to this line from these points. It basically tries to minimize the space between the summation of the space between the predicted Y and the true Y here, right? And that's how regression works. And that thing that just Matt mentioned, the minimizing of the summation of the errors between the dots and the line, that is what we call the loss function. And machine learning algorithms work very similarly to this. They just have a different loss functions from time to time. Anything that any of these algorithms, ranging from regression, logistics, SVM, neural networks, they all have this loss function. And they try to minimize this loss function. And that's how they find the W's. And I don't want you to like fully like look into how the mathematics of that works. But different models are different generally because of this, because they have different loss functions and they have different approaches to minimize that loss function. And that is the main thing that differs them. For example, neural network doesn't really do this sum of all the square errors here. Why is because imagine you have 2 million dots here. How long would it take you to calculate the sum of errors between all the dots? We'll get into that a little bit later, but neural network uses something called calculating gradient descent in smaller batches, which is more efficient than this approach. But the main idea I want you to get out of this slide is that each of these algorithms have a loss function. And all they do mathematically, right, is to try and minimize that loss function. That's about it. And the answer they will give you is the minimized version of that loss function. Now, since we got that, any question on the loss function? Okay. I have another question for you. Imagine we're on this point. Can you see my mouse cursor?
Yep.
Yes.
Assuming the model I built here is true, which is not, it's just a bunch of data during 2 months. Assuming this model is true, would you buy Ethereum at this point?
Yes,
Why?
because Ethereum's price should be on the line.
That is correct. Or as we would say it in the market, it is undervalued.
Yeah.
Assuming we know what the true value is, which is the line here, right? And that's how we would like place a trade here. And like we know that in the future, this dot is going to converge to this line. That will be the idea. Of course, this line could, you know, I have no idea whether it's accurate or not, but the main idea is there. Very good, Valentin. Thank you. Okay. Let's get a little bit more into this loss function. I've mentioned before that each of these ML algorithms try to find and minimize this loss function. The general idea here is that the model works in different ways. We have an algorithm that each step it takes is going towards minimizing that loss function. As I've mentioned before, if you try to calculate the sum of errors for data like more than 100 rows of data, and you want to use the Excel's loss function for regression to do that, that is probably going to take you weeks to calculate. You're not going to be able to do it. Now, what, for example, neural network does is that it uses something called gradient descent, which I will get into a little bit later on. But the main idea is that it will take the data in smaller batches, and it will find the local minimum in those small batches. And it will like put these batches together to find the like global minimum of that cost function. And the general idea for a lot of these machine learning algorithms is that move towards minimizing that loss function in a smarter way than mentioning the whole entire database. Questions so far? All right. Okay, then let's get to our first machine learning algorithm. We're going to talk about support vector machines, and this algorithm can be used for both classification and regression. There was a sort of a semi-theory video I sent you. I didn't expect you to like watch all of it, but it would give you a general idea of what the problem was it was trying to solve. Now let's get to this with an example, right? Imagine we have this data set, right? We have two features, x1 and x2. That's it. Simple as that. And we have two y's. It's either -1 or +1. In other words, it's either blue or red. And we want to train a model here that is able to basically distinguish the blues from the red, or in mathematical terms, it would be something like this. Whereas like we want to draw a line where if you're above the line, because the machine doesn't really understand red and blue, it would draw a line. If the value is above that, it will assign it a 1 value. If it's below that, it will assign it a -1 value. And that's the entire idea behind it in classification. And you want to solve this problem, right? You have this problem, 2 dots red, 2 dots blue, and you want to classify this based on 2 x's. You want to train a model that is able to draw a line to classify this. When I say classify, to separate this. If we look at that line, we're going to be able to understand which one's red and which one's blue if we didn't have the blue and red, right? Based on that line, we'll be able to predict the future reds and blues even if we didn't know if they were red and blue. All right. With that in mind, which one of these lines would you draw? Have in mind the middle one is the line that you have. Like, which one of these lines is better? Imagine you fed this to the SVM and SVM told you, okay, I have 3 alternative lines to separate this data. Which one of this line is doing a better job at separating? Have in mind, I'm talking about the middle line here. Which line would you choose?
The third one,
Yes, why?
because it's equidistant. It seems like it's equidistant between the red and the blue.
That is true. Could you expand a little bit more on that? Why would that be preferable?
Probably the error term would be the same above and below.
That might be true, but think of it as our train sample and test sample. Why would we want to increase this margin?
Are you getting into the overfitting and underfitting?
A little bit.
You don't want to be too close to one
A
side.
little bit. The way Matt, you're absolutely right. The way I think about it is that you want to reduce the chances of being wrong. That's why this like more space is better. Because if you draw this and you go and test this on another sample, you're like, I'm comfortable about this. But if you do this, this might have been an error. The next red might be here. You have no idea where the next red, the actual red is going to be. But with this, your sort of chances of being wrong is reducing. And that's what we call a margin in support vector machines. And one of the goals of support vector machines is to like maximize this margin. It has 2 goals. We're going to talk about the other goal in the next slide. But one of the main goals is that like it wants to minimize the risk of being wrong. It wants to maximize the space between the lines. It wants to separate them as much as it can. Any questions on that? Okay. Now, let's say, okay, it wants to maximize that space, but we don't want it to like maximize it to a point where we're, predicting everything wrong. That's not the whole point of this machine learning thing. So the SVM loss function, as I've said before, the only thing that we're talking about here is like each of these machine learning algorithms are trying to minimize the loss function. The SVM loss function is trying to satisfy and maximize the space between the what we call the margin, constrained by being right, by classifying the whole thing right. And we call this a hinge loss function. And the whole SVM algorithm works to sort of with this dynamic. There's a trade-off. If I sort of reduce my margin, I'm going to be more accurate, but I might have more bias if I'm testing out of sample, right? And the sort of more generalized I'm getting, I'm probably going to have more confidence in my model's performance in out of sample data. And we get to control this trade-off. We get to control this trade-off with a variable called C. It's like, this might seem complex, but coding is super easy. You just like tell scikit-learn a line of code, this is SVM, this is its C, this is X, this is Y, and everything's done like that. It's not going to be complex coding. But the main thing you have here in the SVM is this concept of C. Whenever you're telling SVM to, okay, come classify or do a regression on this data and have a low C value, what SVM will do is it will sort of prioritize the margin space. It will try to, if you look at the picture on the right, it will try to generalize. And I would say this is the better sort of model, because if you look at these 2 dots here, the orange ones, those might just be some extreme examples. It might not even give us much knowledge. It might just be random error in there that we have in our data. So low C value will try to prioritize this, maximizing the margin. But higher C values will try to like increase the accuracy on the training sample. When I say accuracy, I mean the like mean square error in regressions or whatever else we're measuring it by. It will try to sort of maximize that thing, and it will try to be correct as much as possible on your training sample. And that is the different dynamic of the SVM. You basically have a margin and you want to predict correctly. The margin is for generalization, and the predicting correctly is, for good sense, right? And these 2 trade-offs, you want to be able to train a model that is correct, but is also applicable in other data sets. And that's the whole idea behind it. Any questions on this dynamic?
And that's the importance of the loss function, right? That's the key thing, that it's like almost you're training the computer to minimize your losses.
That's true. The computer doesn't understand any of this dynamic. The computer sees the loss function, and the loss function is like designed in a way that like will play this dynamic together. Any questions? Anyone? No?
Is there ever a time that you would want a high C?
Yes. There's like, especially like I've worked with financial data, like we tried to classify Forex trends a while back, like 4 or 5 years ago, and we were using technical indicators. The problem with financial data is there's too much noise. You're not gonna have your cake and eat it too. So like the best accuracy you're gonna get on a like a financial binary classification is gonna be like something 60%, right? And that like 1% increase has a lot of profit in it, right?
Yeah.
And sometimes you're willing to, okay, let's increase the C, hope for the best here, and like test it out of sample. If the complexity is still like working out of sample, that means, okay, the C is identifying the right stuff. And you look at it with like validated with the out of sample tests that you do. But there are ways, whenever you can't really like, whenever you reduce the C, you're getting 50% accuracy. I mean, what else are you gonna do?
True.
Okay, now we talked about SVM in a linear fashion, in a good old simple problem linear fashion. Now, what if our problem is not linear? What if we have like the 94 features and we have like a million different Ys, or we have continuous Ys, right? So I'm not going to get into the math of it, but SVM generally has a tool that is like super simple with this, and it's called kernels. And what kernels do, if you want to look at it intuitively, they basically take your like high dimensional feature space and they map it into a solvable problem using, I think, matrix algebra. I might be correct, wrong on that, but they would transform your problem into a one that is solvable by the classic SVM loss function. And I'm not going to get into it, but there are like generally 3 popular SVM kernels that you can use. And again, this is just a one piece of code that you can just put in and be done with it. And the first one is linear, as we covered here. The second one is polynomial, which I believe you should be all familiar with. The polynomial functions are the ones where you're like you have x to the power of 2, x to the power of 3. That's like the polynomial function. And we also have the RBF kernels as well, which models it a little bit differently. And you can gain some intuition by looking into this, but you might want to get it a little bit deeper if you want to use it for a specific type of problem. But in the end of the day, you generally work with whatever works best in your example, and that depends on your data generally and the problem you're trying to solve.
What does RBF stand for again?
I do not remember. I'm gonna have to look that up and get back to you. Yeah.
No worries.
Any other questions? Okay. Now, as I said before, the coding visit is like ridiculously easy whenever you're trying to code. And I'm using Python libraries here. For the SVM, you just import this SVM. I'm going to go through a coding. I'm going to have sessions and I'll walk through. We'll have a sort of a semi-workshop thing that we can go have together for the coding bit. But the general idea is you import this function from a library that people have already coded all that stuff. You don't need to like write that loss function, none of that, right? And you just define this function and you call it from this library, you define it, give it a C, give it a kernel. Like different kernels have different variables. Like RBF has this thing called gamma. If you're doing a polynomial kernel, you should give it the degree, like is it the polynomial second degree, third degree? And after that, you just fit that to your X and Y, assuming you have your X and Y ready. And you can predict it on your test sample with the model that you train. It's as simple as that, the coding part. Obviously, the more complex your problem becomes, you might want to do a little bit more on that, but the machine learning line is generally the simplest part of this, like solving a machine learning problem. Any questions?
Real quick. So this is like an open source language. Somebody that's brand new to this, how do you know if you kind of grab one of these this code that you're not downloading something that's a virus or something that could destroy your computer? Or like, is there any way to tell that this is a legit code?
So couple of things. I was gonna get into the coding later on, but generally what I would recommend for you guys to code with is Google Colab. And I'm gonna get into this later, like I'm gonna send you all the links and stuff. And Google Colab is like basically like Google Sheets, Google Docs. It's something like it's an online framework you can code in, and you don't really need to install go through all the hassles. And another thing that might be good is the Kaggle kernels, but that might be a problem for another day. And whenever you're doing that, all these libraries that you see here, this is how Python works. Python like generally has a lot of libraries, and it's an open source community. A bunch of people get together, write a library. And some of these libraries are very well known. Like the scikit-learn is like probably the most used machine learning library in the planet, right? And you're comfortable with these. But whenever you get to the you might even find a library that some guy wrote on GitHub that has like 2 views and he's giving you a function to use. In my experience, those are fine as well. There are like ways, it's a review-based process. You can see like this guy has this many stars, so he might be legit. But for the purpose of this class and purpose of like your homework and like the introductory level, you're gonna be fine. No one's feeding you a virus or anything in short.
All right, thanks.
Cheers. Any questions?
Stick to the Google stuff, because they protect it as the first bunch.
Yeah, if you're using Google, it's not even installed on your local machine. So
yeah, that's the important part.
Yeah. Any other questions? Okay. All right, so let's get to neural networks. We talked a little bit about SVM, and now we're going to talk about neural nets. This is probably the hottest algorithm out there now, both in academia and in the industry. Everyone's using it because it's really potent in like modeling large data sets. And it's the basis for what you call deep learning, which we'll touch on a little bit later on. They use this for NLP, they use this for voice recognition, all the image processing you're seeing. All these stuff are neural networks. And we're going to start with a basis of it, which I believe it was shown in that video I sent you guys, the perceptron. So a single perceptron looks something like this. Again, we have a bunch of x's and we want to like model a y here. And we have a loss function or an error function or a cost function. There are different names of it. And again, we're looking to find the best w's depending on that error function. And what a perceptron does is like it will get the inputs, it will assign it random weights. So the first time this goes through here, these weights are determined just randomly out of nowhere, right? And it will put this into a function and calculate the y, and it will feed it through an activation function. Now, what this activation function does, I'll go through it in the next slide, but it will calculate a y in that step, assuming we know what the activation function does. And based on that y, it will calculate the loss function. Then it will try to reduce that loss function and adjust the weights accordingly and do this whole thing again and again until it finds a good error point that it's happy with. As for the activation function, what it does is just introduces some non-linearity to the entire feature space that you have. Why that is important is because generally your classification or regression is not a problem that is solvable linearly. Imagine you're trying to divide the greens and reds in this space. You're not going to be able to do this by just drawing a line. You need a more complex structure. And that's what that activation function generally does. It will introduce some complexity into your model, and it will help the model to find a better fit.
Is that activation function, is it like random at first, or is it using the data like in this on the screenshot on the right to kind of predict what that function should be?
So we have a bunch of activation functions that are popular, like these ones, like Tangent Relu, Logistic Sigmoid, right? I'm going to talk about them in a little bit.
Okay.
But the main idea is like the activation function doesn't do anything itself. What it does is like it will gain these, like we have an x1, x2, and we have a random weights assigned. And it will calculate a function, and it will feed those values, whatever values it has given it, to this activation function. And this will give out an output. And that's just to introduce complexity to the model. It just works better.
So it's like a standardized adjustment per se to the
yes,
model.
but the problem with that is like it's not really that standardized. Like generally, whenever people do neural networks, they're not like, let's use like logistic because theoretically this makes sense. The general idea is that like logistic activation function works well with this problem for God knows why.
So
I'm
let's
sure
go back. Let's go back to the slide before with the green dots.
Yes.
So Brian,
Mhm.
what happens is in the normal kind of regressions, logistical function, ordinary least square, and any of the functions you read, the model is predetermined to what kind of source the data comes from. What are the characteristics? It's called the central limit theorem. What are the characteristics of the data? What happens in neural network, it's a non-parametric model. In a sense, the algorithm understands the data as it reads the data. So there is no specific set of characteristics from which the data comes from. And that is what he keeps calling, and that adds to the complexity, So the older models, right, were much more rigid in forecasting because they assume the data came from a population with certain characteristics. Here, the characteristics of the data is formed as we go along with the prediction. So there's a dynamicness to it, right?
Yeah, okay, that makes sense. Thank you.
Thank you, Chuck.
So if I understand what you guys are saying, what is being shown here is technically I want to say maybe the testing set, and that I'm guessing the testing set would sort of give you guys the predetermined characteristics that you guys said come with the data, and that's how you get the decision boundary.
Look at it this way. Look at it like for now, this is just our training set. For now, like we don't really have a test set. We're looking to train a model, right? And we want this. You're muted, bro.
Yes, training set.
Okay, yeah, this is our training set, and you want to train a model that is able to like sort of distinguish the greens from the reds, right? And you want to be able to extract as much information as you can from your X space, your feature space. And what those activation functions do is that they will increase the complexity of that feature space. It will give you more stuff to work with. Like if you're working in an environment, like if you read any finance papers that they try to prove causality, this goes against their religion. Because mixing all this data together, because you won't be able to distinguish what's causing what. But the general idea is that like the intuition you should have is that this activation function will allow with its complexity for the model to be able to fit nonlinear data. Because if we go back to the perceptron here, right, this will calculate the y based on the x's, right? Now, how do we calculate the y based on the x's? Is it a linear function? Is it a polynomial function? Is it Is it a x to the power of 4? Is it an x to the power of 2? We don't really know this. And we want to find the best one, right? For SVM, that was really quite clear cut because we really like did determine how the SVM was separating this whole thing. But for neural networks, we wanted to be able to find the best fit regardless of whatever the sort of the space is looking like. And we have a bunch of different activation functions here that is going to determine that value that we're being assigned to. For example, like ReLU is just a simple linear one, and it's equal to 0 whenever the value is negative. Like this is very popular because of its simplicity, actually. And we have a bunch of different ones, which I'm not going to get into. Like, for example, this logistic sigmoid is used in the logistic regression. But the idea you're going to have in practice about this is that you have a range of activation functions to use, and you generally depends on your data which one of these things will work best. And you're going to want to try a bunch of them. The idea, like in practice, if you're coding it, that's generally the idea of how it works. But one activation function is really important, and like I want you to like actually know what this does specifically. The one called softmax. This activation function is like extremely important in neural networks because this will convert the values that you're feeding it into probabilities. If you feed anything through softmax activation function, it will give you what's the probability of this class to be true given the inputs. It will give you that value. And this is really important because whenever you're doing neural networks classification stuff, your last layer is supposed to be a softmax layer. That's what the output of the model is to you. It will give you a probability. Let me put this together in the next slide, then we'll go over the questions, right? Okay. So as for the neural network, what it is basically, it's just a hidden layer of perceptrons added. You can have like 50 of these, but we're just going to stick with one layer. Imagine you have that perceptron, right? The one we saw here. The same thing. We have a nonlinearity activation function. It will calculate the output. It has an error. It will backpropagate and adjust the weights accordingly. Now, if we look at this thing, we add this layer of Z, which we call a hidden layer. And this is called a density because all of these cells, all of these perceptrons are connected. Now, if we want to look at what happens here, sort of a little mathematics and a little bit intuitively, what happens is here, for example, in the cell block Z1, we'll get X1, X2, X3, and we'll assign it some weights, and we'll calculate the Z1 here based on the X's we get. And based on, we can calculate all the Z's like that. Now, based on all the Z's we have, we can calculate like Y1. Y1 is like a bunch of weights for a bunch of Z's. And we can calculate the Y's based on the Z. And the model will do this. And at this point, it will calculate a loss function. And it will go back to like sort of improve those weights, to adjust those weights. And I'm going to talk about how that whole process works, the weight adjustment. But the general idea is that this will just add one layer, nothing in the whole process is changed. And generally this works better only because it adds more complexity to the sort of the feature space. There's more stuff for the machine to learn from. There's more complexity in that space for the machine to learn from. And have in mind that all of these layers could have different activation functions and be designed differently. However, your input and output layer should always remain constant depending on your input and output. Now, if you put like 50 of these layers next to each other, or like more than 5 or 10, you'll have a deep learning algorithm. Now, any questions on this before I get to the loss function?
So I have a question.
Shoot.
Do the z's go back to the x's and then the x goes back to the z and then until the error is minimized? Is this?
I'm going to talk about the error. Yeah, I'm going to talk about that exactly right now.
Thank you.
Yeah. Any other questions? Just the design and general design. I'm going to talk about how these weights are like adjusted in a second. Okay. So this is the whole like the golden point of neural networks. I mentioned before, like these weights, the initial, imagine like this machine is trying to like, you have a network and you're trying to assign a weight to this. The weights are generally assigned randomly, right, in the beginning. And you have a loss function. If it's a classification problem, it's generally what we call a cross entropy. And if it's a regression problem, as before, it's like mean absolute error or like absolute score errors or something in that nature. And we have a bunch of different these ones. And you might want to look into it, but these are the most popular ones. And what neural network does, as we mentioned before, calculating the sum of, we're in the first loop, like the weights are added randomly. We have a bunch of random weights and we calculate a y. And we want to see what the error is, right? And we want to adjust those weights based on that. And why we do this in a sort of a loop epochy format is that if we calculate the cross entropy or like absolute error for the entire space for large data sets, that's going to take forever. So we're going to have the concept of taking the data in batches. For example, you take the data in 1,000 and 1,000 batches if you have 10 million data. If you take it in like 5,000 batches. And you grab a batch of data and you try to find the local minimum, the loss function for that batch. Okay. Let's look at this chart and shoot me your questions. I understand this might get a little bit complicated. So you have a bunch of data. You have like 1 million rows of data, and you divide them into like batches of, I don't know, 5,000, right? And you start from a random place here. You start from here, and this is your loss function. Let's say J W1, W2 is the losses you'll have with weight 1 and weight 2, the randomly assigned functions. Your optimal sort of space is the minimum of that loss function is here, but you don't know that in hindsight. What you'll do is you'll take a batch in and you'll calculate something called the gradient descent, which is the derivative of that loss function. And what that derivative does for us, it will just tell us like which way is up and which way is down. That's it. Like it will look at the sign of it and it'll say, okay, if I go down, it will reduce my loss function. And the machine will take a step towards that loss function. And that's what we call a learning rate. After we find out in a batch where is up and where is down, we know if we go that way, that's going to reduce the loss function. The idea is like, how large do you want the step of that machine to be to go into that direction? And that's what we call the learning rate. And after that, the machine will take that step to go to that local minima that I had find in that batch sample. Any questions on that? I'm sure there are questions on that. Please do tell.
Yeah, these things will not become clear in one shot, right?
Yeah.
So we are just kind of taking you a macro view, and then we'll have review sessions. Slowly we'll get into it.
This is
But
the last slide.
Unless you see, this is like a view from the space, So you're going to get a macro view of what's happening before you start working on one particular dimension of it, right? So we are giving you that.
Questions? Okay. So the general idea, if you want to look at it intuitively, what neural network does is instead of like calculating the error for the entire space, it takes a batch of data and takes the data in batches and batches. It will find the local minimum of the loss function in that batch. and it will take a step towards reducing the loss function. And it will do this over and over again through different epochs until it has reached a point where it is happy with the loss function. That
So
is
whatever-
the general idea. What was that?
It keeps taking all this data. Is it ever taking some of the same data from different samples, or is it always taking? I guess at some point you reach a maximum.
How do you mean maximum?
Like, all right, say there was 100 in the population. Is it going to take 10 sets of 10, or could it do 100 sets of 10? It just keeps pulling samples.
So it takes it to, like, imagine you have a sample of 100, right?
Mhm.
What it does is it will take batches of 10, for example. Now you can define these batches. You can define batches of 1, which I don't recommend because, you know, it wouldn't give you any idea about where to go next.
Right.
But you want to take these batches in a sense where it's like the same idea, generalized or like not overfitting and stuff like that. But the idea is like it will take the batches of 10, imagine, right? And we'll take these 10 batches and you define something called an epoch. You don't want your machine to be biased to these batches. So it will take 10 batches, 10 batches, 10 batches randomly. If you're dealing with time series, you have to specify, do not do this randomly. These are all correlated, go in order, right? And it will train this once. And what is called an epoch, like imagine you have 20 epochs, right? Epochs are basically loops over your data where the model is still training. It will do this thing again and again and again from different data points. And it will do this to a point where it is happy with the loss function.
Got it. So it will get to a point where it's almost seeing the same result.
Yeah.
Every time.
At some point, you like the whole idea. I mean, we'll talk about this in the next lecture, but the whole idea is like you want to train a model to a point where you're increasing, because theoretically speaking, you can always reduce the loss function on a training sample. There's like you can reduce it, but at a point in time, the evaluation you're getting on test sample is going to diverge. That means that you're overfitting and you need to stop sort of training the model. That's the general idea.
I have a question.
Shoot.
So whenever you kind of you make samples in your data, you have to be like, how do you make like this should be in one sample? So is it combination, permutation? Like how does that thing work? So how do you take which data points together should make a sample, like some kind of, I don't know, clustering? I don't know, how does that happen?
So you don't really do clustering and you don't really see this part, but you only give the neural network the batch size. If you're dealing with time series, what it would do, it would just like divide it in batches from the beginning, from like day 1 to day like 500 is like one sample, day 500 to like is one, and it will go and one batch, one batch, one batch. And if you're not dealing with like time series, it's actually like preferable to like tell the model to select these stuff randomly. That way your model becomes more generalized. It wouldn't be biased to like one point in the data set. But these are the general two approaches you can go. But the stuff we're talking about, like there are whole literatures about like what is the perfect batch size for this like healthcare problem, right?
And one more thing is, so if this happens randomly, so is it possible that one data point can be in multiple batches or samples? Can that happen? It can
generally
like keep.
You'll see it in different epochs. You won't see it in multiple batches. So we have divided the data into different batches, and your model will go through those batches. But after that, it will do another epoch. Like it will do this entire thing again and again to update those weights. But in the same like epoch, you will not have the same data point in two different batches.
But wouldn't that make it biased if it's not random anymore, right?
What?
If in one epoch you do not go over the same data point, would that somehow make it biased? Because
no,
you're not forgetting about
go over the same data point. Because what you want to do is like in the following epochs, you want your model to generalize. You don't want if you look at this feature space, like imagine if you have a local minimum here, like in this point, you don't want your model to be stuck here. You want your model to find its way through different epochs to get here. You want your model, like, that's what I was going to talk about here. Like, the general idea is that, like, imagine you have a bunch of weight and you assigned random weights here, and you're here. This is your loss function, right? And you want to get here. This is the global minimum, right? And if your learning rate is too high, if you take that step too high, you'll miss your global minimum. If your learning rate is too small, you'll get stuck here, and you don't want to do that. And the right learning rate is here. And there are like a bunch of algorithms trying to optimize each of these things. Like, for example, for the learning rate, we have a whole bunch of different stuff that would try to optimize it automatically and dynamically and like adjust it. For batch sizes, I'm sure there's a lot of stuff there to like what batch size to use for this different type of problem. But things like, it is absolutely okay to be confused by these stuff, because they're like an ongoing literature about like what sort of design works best for this type of problem and why. And that is absolutely okay. But these are just parameters that you have to set in your implementation. You have to think about it. Because generally speaking, for example, the batch sizes, the smaller you get, the higher fitting accuracy you're going to get in the smaller batch size, because it's easier to fit on a 5 data points than like 1,000 ones, right? Same idea. But the smaller these are, your computation time increases, and you might get a load of bias. You might just like predict, though, based on the 5 points, it might not be an accurate representation of your entire data space. Does that make any sense?
Yeah, it was helpful, but my concern was if there's a lot of different global minimums. I mean, there's a lot of global minimums and they're all the same. If you choose one and then you would forget about all the other ones because you would think they're the same, is that?
So, I mean, there is only one global minimum, right? We
Yeah,
have a
but there are
lot of
different
local
ones,
minimums. We have a lot of local minimums. That is correct.
Okay.
And your point is absolutely true. Like, we can get stuck on a local minimum, and we might never find the best answer. That can definitely happen. There are like algorithms trying to prevent that, right? Like, for example, like optimizing this learning rate will like sort of keep you from doing that generally. Like, they have optimizers that will adjust this learning rate so you would miss it. But it's absolutely a possible thing that you come and get stuck here. Imagine this is your loss space, right? And these are different weights, and you're here. There's like, if you have a higher learning rate, you can come and get stuck here. You will never be able to get out of here, because like it will not be able to find this. And you get stuck here and you will not get the best model possible. That is definitely a possibility. The idea is that like your model's not always going to work. And the whole like challenge of machine learning is not like coding the thing. It's like these sort of problems. Okay, why is it not working? How can I make it better? What are the things I can touch? What are the different design? Maybe if I add a layer, it would be better. And finding that thing. These are all the questions that are like, some of them are even open questions. And it differs depending on the problem you're trying to solve. The finance problems are different from the healthcare problems considerably, right? And it all depends on those sort of stuff. I don't know I hope that was sort of helpful.
That's helpful. Thank you.
Yep. Any other questions? We're done with the slides. Any questions I will take. We're going a bit over time as well. I will wrap up neural networks in the next lecture. We're going to get over the spring, after the spring break. But
yeah, and during the spring break, let's kind of figure out